Hello, and welcome to our class 3. Class 3 on the syllabus deals with correlation and simple regression, and that's what we'll be talking about today. Well, again, we've divided this up into 2 slides or videos, sets of slides or videos. The first video will deal with correlation, and the second will deal with simple regression. So this is a very natural split. So the first will be correlation, the second will be simple regression. Correlations. What is a correlation? Well, correlation simply represents the strength and direction of the association between 2 variables or 2 sets of variables. By direction, we mean, is it a positive or negative relationship? Not does X predict Y or does Y predict X. We don't mean direction in that sense. We mean direction in the sense of, is it a positive or negative relationship? And of course, it's always important to keep in mind that correlation is not causation. Now, we usually indicate correlation with an R, a letter R. Also, the correlation we normally use is the Pearson product moment correlation coefficient, but of course there are others. For example, if we have 2 variables, there's a number of others, including the bivariate correlation and the biserial correlation and the point biserial correlation. If we have 3 variables, we can talk about partial or part correlations. If there's 2 sets of variables, so more than one variables that we're correlating 2 sets of variables, then we have what's called a canonical correlation. You don't see too many people do or calculate canonical correlation anymore, but maybe 20 years ago, 30 years ago, 40 years ago, it was quite common to see people talking about the canonical correlation. I don't know why that's fallen sort of out of favor. Okay, the correlation coefficient then. Again, it has a name, a very specific name. So the correlation coefficient we usually use is called the Pearson product moment correlation coefficient. Interestingly enough, we usually don't use its full name, right? I mean, it's sort of like tissue. We just call Kleenex. Actually, this is Kleenex. So tissue we call Kleenex, or Kleenex we call tissue. And other things that aren't Kleenex we often call still Kleenex. With the correlation coefficient, it does even a lot of times we don't even say its name, but the correlation coefficient we're usually calculating is the Pearson product moment correlation coefficient. So it does have a name. And again, there are other correlation coefficients other than the Pearson product moment correlation coefficient. Okay, we do have formulas for the correlation coefficient. Fortunately for you, I'm not a work them out by hand or even work them out by Excel person. I don't expect you necessarily to memorize these formulas. You won't be tested on them. They're simple. On a computer, you just press one button and it gives you the correlation coefficient. There's calculators these days that'll calculate the correlation coefficient. So we're not going to worry about memorizing formulas or working out formulas by hand. But there is a theoretical correlation formula. That's what's given right up here. And there is a z-score correlation formula that's given right here. Well, if you look at the z-score formula, you can see that the correlation between x and y, so we write r as the symbol for the correlation between x and y, so this is a correlation between x and y, is equal to the sum, and we're summing across individuals or participants or cases or subjects. So we're summing across people. It's the sum of the cross product of x, of the standardized cross product of x and y. So it's the sum of the z-score for x times the z-score for y for each person. So we take the z-score for x and the z-score for y for each person, multiply them, sum them across all people. We get a sum, and then we divide by n. And that gives us the correlation coefficient. Okay? Field also gives us a formula for the correlation coefficient in terms of covariances. You can see that Field's formula is R equals the covariance of x and y divided by the standard deviation of x and y. So it's the covariance of x and y divided by, this is the standard deviation of x times the standard deviation of y. That's the same as this formula. You'll note one thing about this formula. You see there's a difference between the last slide and this slide. In the last slide, I told you could divide by n, and in this slide, I'm saying n minus 1. You might be wondering what the difference is. Well, the difference is one is a population formula, and the second one is a sample formula. So you need to be aware of this. Normally, we're going to be calculating the sample formula. So normally, we're going to be dividing by n minus 1. But when you get to, for example, psychometrics or tests and measures, you'll be dividing by n. And now, what's the difference? Well, the difference is whether, again, you have a whole population or not. Or some people would argue if your n sizes are so large, there's going to be no difference between n and n minus 1. So if you have a really huge n size, whether you divide by n or n minus 1 is not going to make much difference. But usually, or not usually, but what is typical or standard practice is for the sample correlation coefficient, we're going to express it as dividing by n minus 1. And for the population correlation coefficient, we would just divide by n. So that's the difference. With samples, we're dividing by n minus 1. With populations, we're dividing by n. Again, most statistical software will do that automatically for you. So, for example, when you're a lot of psychometric or test software will use n rather than n minus 1. But that's something you just need to be aware of. There's a slight difference between the sample formula for the sample correlation coefficient and the population correlation coefficient. It only really makes a difference when the sample size is small, because again, if the sample size is very large, so large that n is almost the same as the population, then the difference between n minus 1 and n is negligible. But when the samples are smaller, then there will be a big difference between n and n minus 1. So that just explains the difference between those formulas, the use of n versus n minus 1. Okay, again, the correlation coefficient is then simply a standardized covariance between x and y. You can standardize it by dividing by the two variances, or standardize it ahead of time by using z-scores and using the second simpler formula. So the correlation coefficient is simply a standardized covariance. What's the relationship between the regression coefficient and the correlation coefficient? A good question to ask, because we'll be talking about regression later. There is a relationship, of course. The relationship between the sample regression coefficient, B1, and the sample correlation coefficient, R, is that R is equal to B1 times the standard deviation of x divided by the standard deviation of y. So there is a relationship. R is equal to the regression coefficient, the simple regression coefficient, times the standard deviation of x divided by the standard deviation of y. It's also true then if we use the standardized or regression coefficient, or what we often call big B or beta, then R will equal big B or beta, or the standardized regression coefficient. So with correlation or regression, again, if we're calculating beta or big B, it will equal R or the correlation coefficient. And again, that's if we're talking about a simple regression with only one variable. Okay, so the Pearson product moment correlation coefficient, or R, is probably the most used and important statistic in measurement. Why? Well, because we use it in a lot of things. We use it in reliability estimates, including estimating the standard error of measurement. We use it to estimate validity. We use it in item analysis. We use it in meta-analysis. We use it in factor analysis. We use it in utility analysis, and much, much more. What factors affect the Pearson product moment correlation coefficient? Well, sample size, of course, or stability. You actually need pretty large samples to get a stable correlation coefficient. So until you're getting sample sizes of about 100, you're not going to have a very stable correlation coefficient. Marginal distributions. We talked about this last time. If your distributions of your variables are not similar, it's going to put a limit on the correlation coefficient. Your correlation coefficient can be higher when the distributions are similar, especially if you have a lot of skewness or kurtosis. So similar distributions are going to allow for higher correlation coefficients. Linearity. There must be a linear relationship between the two variables, at least between the asymptotes. And again, we talked about that last time. Subpopulations. If you have subpopulations with different correlations, for example, you have males and females in your study and they have different correlations, then you're going to have different, then that's going to affect the calculation of a single correlation coefficient. Homogeneity of variance, or skedasticity, or homoskedasticity. So again, for the correlation coefficient, we're assuming homoskedasticity. And homoskedasticity again, well, let's see if you can remember. I'll give you a second to see if you remember what it is. Hopefully you answered that. That means that at different levels of x, the variance of y is the same. Or at different levels of y, the variance of x is the same. So that's what homoskedasticity is. It's similar homogeneity of variance of the variable at different levels of the other variable. One of the biggest effects on the correlation coefficient will be restriction of range. You can have there, and this is a huge problem, whether you have direct or indirect. It's a hard problem to solve. We're not going to try to solve it in this class, but it's why before I talked about how it's much harder to actually calculate a population correlation coefficient than you might think, because sample correlation coefficients are going to be impacted by restriction of range. And the more restriction of range there are in the variables, the more, of course, the correlation coefficient will be impacted. Not only that, you can get strange types of restriction of range. So strange or unusual types of restriction of range can almost make your data look like it's non-monotonic rather than linear. And in that case, of course, it'll affect the correlation coefficient. And then, of course, a big effect on the correlation coefficient is unreliability of x and or y, really. If either x or y are unreliable, it's going to place a limit on the correlation coefficient. As a matter of fact, we know that that limit is the square root of the reliability of x, or the square root of the reliability of y, or the square root of the reliability of x times y. That's going to be the limit on the correlation coefficient. Fortunately, we can correct for that unreliability. It's called the correction for attenuation. Again, one of the interesting things about the correlation coefficient is that, and one of the reasons it's so used, it actually partitions variance. It partitions variance into two parts. It partitions variance into what's called explained variance, or R squared, or that's actually given a name, the coefficient of determination. And it partitions variance then into unexplained variance, which is 1 minus R squared. So the correlation coefficient partitions variance into two types: explained variance in y by x, and that's given by the coefficient of determination, or R squared, and unexplained variance, which is given by 1 minus R squared. Okay, we mentioned there's other types of correlations. In addition to Pearson's, which is the main types of correlations are Pearson's R, which is the correlation between two continuous variables. Spearman's P or rho. That's really a rho. I'm not the best at Greek symbols, but I believe that's a rho, which is the correlation between two ordinal variables, or one ordinal variable and one continuous variable. And Kendall's tau, which is the correlation between two ordinal variables with many tied ranks. And that's an alternative to Spearman's rho when there are many tied ranks. And of course, then there's also a lot of other inter-rater correlation coefficients. So there's a lot of other inter-rater correlation coefficients. Here are some more or additional names for the correlation coefficient. I mean, this has a weird and strange history. Part of the reason we have different correlation coefficients is that at one time people did have to calculate correlations by hand. And if you're calculating them by hand, some correlation coefficients are easier to calculate using adjusted formulas, especially if you're doing it by hand. So one of the interesting things about this table here is that in two cases where it says uncorrected, the correlation is really just a Pearson product moment correlation coefficient. It's going to be the same, but there's a simpler formula because of the nature of the data. So we have here, we can see the different these are the different names. And this is what it corresponds to. So if we have one dichotomous variable and one continuous, again, a dichotomous variable is one that can only take on one of two values. For example, correct, incorrect, true, false, high, low, senior, senior, younger, whatever you want it to be. If we have one dichotomous and one continuous variable, then we can calculate a special correlation, or the correlation has a special name because it does have a special formula, and that name is the point by serial correlation. But the point by serial correlation is actually a Pearson product moment correlation coefficient. Now, it is possible to correct this correlation for the fact that one of the variables is dichotomous, and say, what would the correlation be if this variable was actually continuous? Because it would normally be higher. And that correction, or that variable also has a name. That correlation coefficient has a name. And the name of that correlation coefficient is the biserial correlation coefficient. Then we can have two dichotomous variables. If we have two dichotomous variables, again, we have a special formula for the correlation, the Pearson product moment correlation coefficient. But it's still a Pearson product moment correlation coefficient, really. But that is then, and it depends, I guess, depending on whether you're English or from the United States, depending on where you were schooled, depending if you went to a sorority or fraternity, you might pronounce this differently. But phi or phi, or however you want to pronounce it, phi or phi. So the phi or phi correlation is a Pearson product moment correlation coefficient, but it's a specialized formula for the situation where two of the variables are dichotomous. The two variables are dichotomous. Now, if we move to a situation where we say, hey, what if those two dichotomous variables were actually continuous? Then we have another name for the correlation that we calculate. This is one where we correct the dichotomous variables to say, what if they were continuous? And it's called the tetrachoric correlation. The tetrachoric correlation. So those are alternative measures of association. So right now, all I'm pointing out to you is there are correlations other than the Pearson product moment correlation coefficient. Although actually, two of these will give you the exact same result as the Pearson product moment correlation coefficient. So we can see if we look at, again, some of these measures, if we have a true dichotomy, we're either dealing with the phi or phi or the point by serial. If we think there's an underlying continuum, there's the tetrachoric and the biserial. We also have Spearman's rho, Kendall's tau, and there's something called the eta coefficient as well. There might be times where you say to yourself, I have two correlations. Are they the same or are they different? Can I test for differences between correlation coefficients? There are some methods for doing that. One of the most common methods is what's called the Fisher R to Z transformation. That then leads to a Z-test on whether the correlations are different. If you go online, there's online calculators. For example, for independent correlations, there's an online calculator you can find. For dependent correlations, dependent would mean for example, repeated measures. There's a online calculator as well. So there are ways to determine are two correlation coefficients the same or different. Probably the most common method is the use of the Fisher's R to Z transformation. All right, we're going to turn to Fields now. If we turn to Fields, Fields talks about how to conduct a correlational analysis. You can see Fields says the first thing you should do is check your assumptions and bias. Do we have linearity? Do we have normality? And again, those could be checked using SPSS Explorer or various graphs. If the assumptions are met, then we can use Pearson's R. If the assumptions are not met, we can use a non-parametric test, such as Spearman's rho or Kendall's tau, or we can bootstrap our confidence intervals or confidence limits for R. But probably in most cases, even if the assumptions aren't met, you're often going to be using R. If you have outliers, I would assume maybe you're just removing the outliers. And if you have ordinal data, well, then maybe you better go back and remeasure things. Okay, so to get a calculation in R and to get a correlation or an R in SPSS is extremely easy. We just go to analyze and then to correlation, and that'll take us to bivariate correlations. And all we have to do is bring in to the variables box those variables that we want to correlate. We can ask for various options. It's good to ask for means and standard deviations. We can bootstrap our confidence intervals by using the bootstrap option. You'll note Field almost always uses the bias corrected accelerated as the option for his bootstrapping and uses simple sampling. Also, I should note here, we're calculating a Pearson's correlation coefficient. We're testing for significance using two-tailed tests, and we're flagging the significant correlations. So once we enter all this in, hit continue here, continue. So we would hit continue here, and then we would hit OK, and it's going to calculate the correlation coefficient. So here's the correlations that we get calculated from Fields data. We have three variables, again, time spent revising, exam performance, and exam anxiety. And you can see here we have our correlation. So for example, the correlation between time spent revising and exam performance is 0.397. The p-value or significance level associated with that two-tailed is 0.000, and there's 103 subjects or participants. For time spent revising and exam anxiety, the correlation is a negative 0.709, very high. It's significant at the 0.000 level, so very significant. You can see that the significant ones have been marked. These two asterisks here and two asterisks here indicate that the correlation is significant at the 0.01 level. If it was significant at the 0.05 level, there would be one asterisk. And you can see we also get our bootstrap bootstrap results. And so the bootstrap results are the 95% confidence interval for the correlation. Now, I don't know if they went through this in stats one. Of course, there's differences in how people think confidence intervals should be interpreted. Normally, we would say that the population confidence interval does not move. So that this confidence interval is really a confidence interval on what happens when you pull different correlation coefficients from this data set. As a matter of fact, that's exactly what it is. So now, if we're pulling different correlations from this data set or from this population, 95% of the time, that correlation is going to fall between 0.245 and 0.524. So 95% of the correlations fall between 0.245 and 0.524. For exam anxiety, 95% of the correlations that we would obtain, the sample correlations, would fall between negative 0.86 and negative 0.49. Now, the population correlation coefficient doesn't really move around. I mean, if that makes sense to you from philosophy of science, population data does not have randomness associated with it. It doesn't move around. However, a lot of people do talk about the confidence interval as including the population value. So some people might argue that we're 95% confident, or maybe a different word, credibility or something like that, although credibility can have another meaning. We're 95% confident that the population correlation coefficient falls within this range. That's an interesting philosophical discussion. Technically, again, this is the 95% of the sample correlations are going to fall within this range. But again, it's often interpreted, although it's not perhaps purely correct, that there's a 95% chance that the population correlation coefficient falls within this range. And then Field, which is very nice, one of the reasons I like the book, gives you an example of how you might report these results. So you'll note that Field's reporting the correlation coefficient and the bootstrapped confidence interval. I will say one of the things, of course, Field really doesn't, I think, talk about is that to really estimate the population correlation coefficient, we would want to then adjust these correlations for attenuation or lack of reliability, and also any restriction of range. So these probably really are not pure is a bad word, but these are not the best estimates probably of population correlation coefficients yet, because if we really wanted to estimate the likely population correlation coefficient, we should correct for unreliability and correct for restriction of range. Okay, things to know about the correlation coefficient. Again, it varies between -1 and +1. 0 indicates no relationship. +1 indicates as one variable increases, the other variable increases. -1 indicates as one variable increases, the other one decreases. It has an effect size. So we often say correlations around 0.1 are small effect, correlations around 0.3 are medium effect, and correlations around 0.5 are large effect. You know, typically in psychology, we often talk about a 0.3 ceiling, with the medium effect being about the highest correlation we often obtain. Now, again, this isn't a class of meta-analysis, but one of the things that the meta-analytic people point out is that these correlations, again, are probably too low in that they're not correcting for attenuation or restriction of range. Of course, then you would argue if you do correct for attenuation or restriction of range, these effect size labels no longer apply because we're going to be pushing or moving all of our correlation coefficients up. So if we correct for restriction of range and attenuation, all of our correlation coefficients are going to be higher, which probably means then we should adjust these effect size labels as well to reflect the fact that the uncorrected correlations are underestimates. So again, these are effect size labels for uncorrected correlation coefficients. For correlation coefficients not corrected for restriction of range or attenuation. And we mentioned before the coefficient of determination, or R squared. By squaring the value of R, you get the proportion of variance in one variable shared by the other, or predicted by the other, you could say. So, and the correlation is non-directional. So you're both predicting y from x and x from y, although theoretically that might not be the case. The correlation coefficient itself is non-directional. By non-directional, I don't mean that a -1 doesn't mean as one variable increases, the other variable is decreasing. Again, by non-directional, I mean that we're not saying which variable predicts, causes, or is the one influencing the other variable. So correlation and causality. Of course, the problem is we know correlation is not causation. You know, people say that all the time. There's a third variable problem. In any correlation, causality between two variables cannot be assumed because there may be other measured or unmeasured variables affecting the results. And direction of causation. Again, as I just said, and Field is saying the same thing, correlation coefficients say nothing about which variable causes the other to change. Or even it could, again, be neither variable causes the other to change because there's a third variable involved. Again, I mentioned correcting for attenuation and correcting for restriction of range. The formula for correcting correlations for attenuation is quite simple. The corrected correlation is equal to the obtained correlation between x and y divided by the square root of the reliability of x times the reliability of y. If you take tests and measures or a psychological measurement class, you probably go over this. If you take a meta-analytic class, you go over this for sure. But again, the corrected correlation is going to be equal to the original obtained correlation between x and y divided by the square root of the reliability of x times the reliability of y. And that gives you your adjusted population correlation coefficient, which, unless you have something really odd going on, well, unless you really have something odd going on, it's going to be higher than your original obtained correlation. Now, we have not yet adjusted for restriction of range. Adjusting for restriction of range is too hard of a topic to cover here. I thought of giving you an article on correcting for restriction of range. I didn't because, again, it's just a topic really beyond the confines of this class. Okay, this is just from Field, and it's showing you again it's a diagram to show you the shared variance. I'm not going to say a lot about it. You can go into Field's book and look at this nice diagram he created and his explanation of it showing you shared variance. Okay, I mentioned before there's also something called partial and semi-partial correlations. Those, of course, involve a third variable. Actually, the calculation of partial and semi-partial correlations is important in regression. A partial correlation is just the relationship between two variables. adjusting for the effect that a third variable has on them both. So a partial correlation is if we have two variables, x and y, and we have a third variable, z, we adjust for the effect of z on both x and y. With the semi-partial correlation, it's a measure of the relationship between two variables while adjusting for the effect that one or more additional variables have on one of those variables. So if we call our variables x and y, it gives us a measure of the variability that y and x alone share. Okay, so it's the relationship between two variables after we've adjusted for the effect of one or more additional variables on that one variable. The one variable usually being the y variable. But so a semi-partial correlation, it's what effect that variable has after we adjust for the effect of other variables on one of these variables. And that's going to be important in regression analysis. Now again, SPSS has an option where you calculate partial correlations. When we perform a regression analysis, we'll be calculating these correlations as part of the process of the regression analysis. So this shows us how to do this is from Field again, it shows us how to do a partial correlation. To do a partial correlation, we would just put in the two variables we want to correlate, in this case exam performance and exam anxiety, and then we put in the variable we want to control for, which is time spent revising. So that's the control variable. We have certain options. We can do zero order correlations. We can do means and standard deviations. Even though Field hasn't done means and standard deviations, I always like to do means and standard deviations. Again, we have two-tailed tests, and we're displaying the actual significance level. We would hit OK, and if we hit OK, it'll move on and do the calculations. Field shows you here the calculations. So this is showing you the correlation between exam performance and exam anxiety after we control for time spent revising. And again, this is a partial correlation. So we're controlling for time spent revising in both variables. So after we control for the effect of time spent revising on both exam performance and exam anxiety, we can see the new correlations. So the correlation between exam anxiety and exam performance is now a negative 2.47 after we control for time spent revising. That's still significant. The significance level is 0.012 two-tail. We have 100 degrees of freedom. And here are, again, our bootstrap confidence intervals. I guess it's sort of cut off here for exam anxiety by my picture. We're now going to leave Field's data sets and turn to our own data set, or the data set I created, the COVID data set. Again, there's 50 states in this data set, 51 if you include District of Columbia. You'll notice I switch back and forth a little bit. For this analysis, though, we are eliminating District of Columbia. So I did eliminate District of Columbia for this analysis. As I said, it was sort of a strange outlier on a number of variables, so I eliminated it. Also, one thing as we go through, you'll note sometimes I express the COVID deaths per 100,000 and sometimes per million. I'm not a very obsessive compulsive person. I had in the data set both the COVID deaths per 100,000 and per million. They're usually reported per million by the World Health organizations that report data, but a lot of the other data was in 100,000 or per 100,000. So I put both in the data set, but then I switched back and forth, which I used as a dependent variable. It doesn't, of course, matter, but I just wanted to make you aware of that. So here's some descriptive statistics from our data set. COVID deaths per 100,000. The mean is 91 deaths per 100,000, about, with a standard deviation of 44. A pretty large standard deviation, you'll note. The average age, now this is not the average age of death, this is the average age of people in the state. So the average age of people in the state is 38.73 for all 50 states, of course. The density per mile, that's the amount of how many people there are per square mile, basically. And the mean is 198. The temperature, that's the average temperature for that state for the year, a mean of 51.94. The death rate per population. Now what that is, and that's again per 100,000, that's how many people in that state die from all causes. And I went back a couple years to get that. So I think that's from around 2015 for each state. And I thought that might be an indicator of general health or wellness in the state. And so I put that in as a variable, the death rate for the state per 100,000. Nursing beds per 100,000. You know, there's an indication that a lot of deaths occur in nursing homes. So I did nursing beds per 100,000. And then there's been hypotheses and political arguments that minorities, in particular African Americans, are more impacted by COVID for a number of reasons. So I also put in for each state the percentage of people identifying as African American or Black per 100,000. Okay, so that's our basic data. And then since we're dealing with correlations, I calculated correlations to see what correlated with COVID deaths per 100,000. And you can see, if you look at this chart, if you can see it, what this chart shows you again is each variable, the Pearson correlation coefficient, the probability value or probability level associated with that correlation coefficient, and then, of course, whether it's significant at the 0.05 or 0.01 level. One asterisk is 0.05. One asterisk is 0.01. I'm sorry. One asterisk is 0.05. Two asterisks are 0.01. If we had three asterisks, it would be 0.001. And of course, the n size. But the n size is 50 for everything. We don't have any missing data. The thing I'm most interested in is COVID deaths per 100,000. You can see average age is not significant, at least at the state level. So the average age within the state is not a significant predictor of COVID deaths. The density is. Density is a pretty highly correlated, 0.45. The probability level associated with 0.545 is 0.000. So it's obviously lower than that, but 0.45. So density per mile is a pretty good predictor of COVID deaths per 100,000. We'll be using it later on. Temperature, and this again is the average temperature in the state, 0.095, probability level 0.510. So not really at least we can't say that it's a significant predictor at this point. The overall health or wellness of the state based on the death rate per 100,000, almost close to zero, negative 0.015. Nursing beds per 100,000 is a predictor, 0.469. And also the percentage of individuals identifying as Black in the state in terms of their race is a predictor of COVID deaths per 100,000. So when we look at this, we can see what variables are correlated, and at least on the surface then might predict COVID deaths per 100,000. That's interesting in and of itself, but of course we'll be using it later on when we go through the regression analyses. Okay, so we want to keep this sort of chart in mind later on as we go through our regression analyses, although we'll also have other variables. And that's the end of our correlational section. Our next section is going to deal with simple regression. Thank you for being patient and sitting through the correlation lecture. I would think you might have a lot of questions. Unfortunately, this format doesn't allow for questions. It doesn't allow me to see when you're confused or don't understand what's going on. So please bring your questions to the discussion section. Thank you very much. And the second part of this third week of class will deal with simple regression.